Recording in progress.
Yes.
Please, dear friends, it's time to start the last session of the seminar number 1. Dmitry Voronin join us in a couple of minutes. The first speaker, Boris Lukyanchuk, Moscow State University, and he is going to talk about magnetic fields generated by light in dielectric particles. Please, Boris.
Okay, thank you very much. Do you listen to me?
Yes.
Okay. First of all, I'm very thankful to Olga for this invitation. And I want to start with some historical... Why switch?
Yes. Okay.
In fact, it is well known, at least for a few thousand years, that transparent particles or transparent spheres can focus light. It was so-called magic crystal. And druids know it a few thousand years ago. Pliny the Elder mentioned about this effect of light focusing in his encyclopedia 2000 years ago. But physical origin for this effect was not known. The same like effect of light refraction. All the scientists like Archimedes, Ptolemy, and all the ancient scientists know effect of light refraction, but to establish correct law for light refraction, it took at least 1,000 years. And first time it was done by Ibn Stach near 1,000 years. Then a chain of discoveries was first was Thomas Heriot in 1602, then Johannes Kepler in 1604, Snellius in 1621, René Descartes 1637. In France, this law of light reflection is called like Snell's Descartes law. Then in 1662, Fermat established this law of light refraction from the principle of Fermat principle of that light goes by trajectory which need the minimal time. And finally, Huygens in 1678, he showed that it falls from the wave nature of light. So when Galileo did his invention of telescope, he used typical lens, and up to recent time it was from side of centimeter scale, maybe up to millimeter scale later in microscope. But he did not understand the origin of how this telescope works. And this work was done by Kepler. Kepler, he introduced the meaning of focus and explained the principle of pinhole camera. And in his book published in 1611, he described light refraction and the concept of the optical image. He yielded also the general theory of lenses and suggested ray tracing method. In fact, it was geometrical optics. So he was a father of geometrical optics. he did not do this one for spherical particle, but he did it for thin lengths. But no doubt that he was able to do these calculations, and if he did this ray tracing, so using refraction of light here in light enter and go away the spherical particle, then he was able to find caustics, and I think that he was able even to analyze theoretically intensity. He did not do it, but he was able to do it. And if he did these estimations, then he found that intensity in caustic does not depend on the particle size, but it depends on the refractive index only. And with refractive index by the order of 1.6, you can see intensity enhancement 50 times or even higher. Then next step was done by Lord Rayleigh, who analyzed the scattering of small dielectric particle with size much less than radiation wavelengths. And result was that this particle scatters like a point electric dipole. And it is non-resonant scattering. The scattering efficiency is given by this formula where Q is so-called size parameter, ratio radius to lambda multiplied to 2 pi. In 1908, Me published his paper about Me theory. He was not the first, at least 7 people before Me obtained the same formulas, but he did physical discovery. He paid attention that scattering may have resonant nature, like here it is shown. If we will divide scattering efficiency to size parameter with exponent 4, then it is function of refractive index only. So for Rayleigh scattering, it tends to some constant, like 8 to 3. But in the case of Me scattering, we can see huge resonance. It depends on the refractive index at the size parameter. And from the Me theory, it is applicable for any size, from very small to very big size application of geometrical optics. So from the Me theory, it is easy to obtain this Rayleigh limit that is just from this formula with L equal 1 and only with electrical dipole. And from this consideration, we can see that Rayleigh scattering is not only non-resonant, but also non-magnetic, because magnetic amplitude is all the time much smaller than electrical amplitude. It is more complicated to analyze limit of geometrical optics. For this case, it's necessary to calculate this Bessoid integral, and mathematicians like Michael Berry did this work, and finally, in the paper of Johannes Kofler and Nikita Arnold, they found when this me theory corresponds to geometrical optics approximation. So it depends on the refractive index. For example, here for refractive index, I forgot 1.5 for glass. You can see that with size parameter equal 10, we can see difference between me theory and approximation of geometrical optics. The same, we can see difference at size parameter 30, and finally, just when the size parameter became 100 or even higher, 100, then we obtain good agreement, me theory and geometrical optics. Now, if we combine all of these limiting cases, you can see that for small size parameter, that is case of relay scattering. For big size parameter, that is approximation of geometrical optics. And with size parameter by the order of unity, we have region of so-called me resonances, where people, which is quite important for modern nanophotonics, where people basically are interested in first resonances like dipole, quadrupole, octupole, and so on. But between region of me resonances and geometrical objects exists some other area which is called now meso-optics with size parameter by the order of 10. It corresponds variation from 10 to 100 or ratio radius to lambda from 2 to 10. And in this area was found a lot of new physical effects, starting from photonic nanojet, magnetic light, film nanoscopy. I have no time to discuss all of these effects, so I will concentrate only on the ability to create huge magnetic fields during scattering. So in 2010, two groups published paper that it is possible to create huge magnetic moment even with small particles. It is necessary only to have sufficiently big refractive index, for example, refractive index higher than 2. And this theoretical predictions was quite fast, checked experimentally. Also, a few groups show this one that we can create, except of electrical dipole, you can create magnetic dipole. And it was quite important discovery, but because when you have together electrical and magnetic resonances, you can control light, you can control directivity, and it was shown quite fast by a few groups from Spain. They show microwave. Our group show this effect in visible range, and group of Novotny show that it is possible to do in infrared region. So changing wavelengths, we can create or forward scattering or back scattering due to Kerker effects. And it gave ability to produce high ratio, for example, forward to back scattering or opposite back scattering to forward scattering. Then it was the basis for all dielectric resonant nanophotonics with sufficiently small particles of nanometer scale. And it was shown that it is possible also to control phase with these particles, and it has many applications. Now, I want to remind you story with high magnetic fields. Here is order of magnitude of magnetic fields in surrounding nature. For example, that is strength of Earth's magnetic field on the level of 10 to minus 5 Tesla, till to Planck magnetic field in the theory of superstrings, which is 10 to 53 Tesla, and even smaller amplitudes of magnetic fields can be seen in general theory of relativity, for example, frame dragging effect from rotating gravity like Earth with rotation. Now, to use high magnetic fields, in 1924, Kapitsa, he was working at that time in laboratory of Rutherford, he received a magnetic field with induction of 1 million Gauss, that is 100 Tesla. He used solenoid, and till to 50s, it was some record values for magnetic field. But in 1951, Andrei Sakharov suggests the idea of magnetic flux compression generator, and such generators permit to obtain fields about 3,000 Tesla. That is the same value which was obtained in Los Alamos laboratory in Russia. So that is a long-standing problem of generation of high magnetic fields with a field strength above 3,000 Tesla, which present a human record for pulsed magnetic field up to now. Now, if we will see me theory and we'll analyze how field varies in different resonances, magnetic and electrical resonances, then we can see that here are shown first 5 resonances for silicon, for example, refractive index and equal 4. That is just because it is convenient to see separately effect of many resonances. What is important that for the case of electrical first magnetic dipole resonance, field enhancement, electrical field enhancement, that is on the level of 25. At the same field enhancement, magnetic field enhancement, that is near 700, 600. So that is a huge difference between magnetic and electrical field. So, and this enhancement of magnetic field increase with higher order resonances with electrical, magnetic, and so on. So idea was, it was shown experimentally that if you will take, for example, 2 cylinders, then between cylinder you can see field enhancement. It depends on polarization. If it is polarized in this direction, you can see field enhancement, electrical field, but in perpendicular direction, you can see field enhancement due to magnetic field. And it was done for the first magnetic dipole resonance, so field enhancement was above 10, so magnetic intensity was about 100. Now,
Boris, excuse me, you have maybe 1-2 minutes. Time is almost finished.
Yeah, just.
I think we give more time to Boris. He can speak as much he wants.
Yeah.
Last session anyway. Don't hurry up.
Now I want to mention Descartes. Descartes, he suggested that in the universe, very important role play vortices of light. And it was so interesting that all the people discuss it at that time. And then Newton criticized this idea, but now we know that it is possible that optical vortices can create effect of rotation and effect of mechanical effect. So if we use me theory, then we can find that at size parameter close to 10, one can see it depends on the refractive index also. You can generate optical vortices, and that is some many papers was published this one. One more important component is related to Fano resonance. Fano resonance, it is quite simple interference effect related to interference of two signals with broad and narrow spectrum. And when you have, for example, here you can see for plasmonic particles, this broad relay scattering and narrow quadrupole resonance. And with this resonance, you can create very narrow resonances. And if you will follow two different resonances, then you can see that intensity of magnetic field inside the particle increase drastically with each resonance approximately 1 order of magnitude. However, it needs weak dissipation, like in plasmonics, we need small dissipation. The same effect you can see even with dielectrics. If you will take, for example, silicon and the fifth resonance produce field enhancement, electrical intensity 1 million times and 10 millions of magnetic field. Then if you include dissipation, then you can see that with dissipation of the level 10 to minus 3, this resonance disappears. So you need very transparent materials to obtain these resonances. Now, what is the reason for high magnetic field generation? In fact, it follows from Biot-Savart law. We know that inside the loop, we have magnetic field, which is inverse proportional to radius of this loop. So if we would be able to create small vortices, then we can create huge magnetic field. However, how small can be optical vortices? If you will see 100 dipole resonance, it produces typically 100 nanometers. which is insufficiently small. However, we have super oscillation effect. When we have optical singularity, then around of this optical singularity, we have variation of phase, which is 2 pi around this point, and it creates a huge localization near central point where pointing vector is equal 0. There are no diffraction limit for the duck. You can focus duck beyond any size. It just need no photon. Now, if you compare what you can reach with high order Fano resonances, then it is easy to find that it is easy to obtain 10 to 5 and 10 to 6 and even higher intensities, magnetic intensities and electrical intensities also. So it is possible to create huge contrast of magnetic field to electric field. It means that we can, in principle, it is possible to create magnetic nonlinear optics where variation of the refractive index happens due to variation of mu, not epsilon. Now, so we did this theoretical calculations a few years ago, and I did presentation in Landau Institute, and theoreticians were quite skeptical. They thought that it's impossible to use so narrow resonances to obtain this huge field enhancement. Fortunately, during this presentation, it was some people from Joint Institute for High Temperature, and they invited me in the Institute of Vladimir Fortov, that is our former president of Russian Academy of Science, and I did this theoretical presentation for them to show that it is possible to obtain field enhancement on the level of 10 to 10 or even high field enhancement. And they decide to demonstrate it experimentally. They use for this purpose ceramics in microwave to show that it is possible. It was ceramics on the level of 150. So to see how this electrical magnetic field grows from one resonance to another. And this experimental measurement showed that yes, even for the first resonances for dipole, even for dipole resonances, it is possible to obtain magnetic field 1 million times, for example. So if you use high intensity, then it is possible to create magnetic fields comparable with fields in neutron stars. So in conclusion, I want to say that there are many optical effects rising at intermediate range of size parameter, Q from about 10, including photonic nanojet, nanoscope with super resolution, nanovortices, nanopole states also. And all these effects are related to formation of strong magnetic modes, magnetic light, and interference phenomena. So these strong magnetic modes related to high order Fano resonances and super oscillation phenomena, which permit to create nanovortices with very high magnetic intensities. It have a lot of possible applications for magnetic emitters, magnetic nanojet, magnetic nonlinear optics, nanoscopic, etc. That is all. Thank you.
Thank you very much.
Yeah.
Please, are there any questions? Olga, please.
Thank you so much, Boris. Very interesting result. And so, how big magnetic field has been produced? What is the duration? What is the scale?
We used a ratio of input of magnetic field really measure compared to magnetic field in plane wave. So we eliminate the spherical particle by plane wave, and ratio of focused magnetic field to magnetic field in plane wave. Experimentally, we show that it can be for the first resonances even 1 million times. Then Fortov was very enthusiastic and told that we should publish it in the best Nature paper. And we sent to Nature Energy, but they reject our paper and thought, what you show? You show that you can enhance weak signal 1 million times. That is a different story. If you show really that you can overcome 3,000 Tesla, then we can discuss it. So we are trying now to do with high intensity. That's just asking. No, technology shows that if basic physics is correct, then technology soon or later able to overcome this problem. So I believe that Maxwell equations are correct and solutions correct. And so
let's hope.
And Forta was interesting. He was working with for many years with nuclear fusion, and we know with neutron stars that is stationary oven, which can be stable. So I want to see, is it possible to create small micrometer neutron stars with sufficient energy?
Vladimir, please.
Боренька, привет, this is Vlad Shalaev.
You can see him, by the way. Boris, can you?
And actually, I should congratulate you. You did truly remarkable work. I'm aware of most of this, but just seeing it all together, it's mind-blowing. So basically, this will stay in the history of science. Absolutely terrific work. But I have a small request, which Olga already mentioned. May I actually see you? Because I didn't see you for such a long time.
I want to see me.
Yes, I want to see you.
Yeah.
Hey, but Boris, congrats with your fantastic work.
Yeah, okay, thank you.
Okay, thank you so much. I think we should proceed. Thank you, Alexei, for chairing the second session. I think Dmitry is here and he's ready to take over, right?
Thank you, yeah.
Dmitry?
Yes, thank you, Alexei.
Thanks.
Helping out. Okay, our next speaker can set up the PowerPoint. The Professor Minoni.
Hello, and thank you. That was a very exciting talk. I am going to now try to, if the previous speaker can actually stop sharing,
Boris, you
I'll be
remove
able
your
to share.
slide. Stop sharing, Boris. Boris, can you hear us?
Yes, I can see you, but I cannot switch off this.
Stop sharing. You should just close your slides.
That's what I'm trying to do. Yes. Yes. Oh, okay.
All
Thank you.
right.
Okay. Yeah, sorry.
That's all right.
Well, it's great to be here. And thank you for the invitation to the organizers, especially Olga. So what I am going to talk to you about is a slightly different topic, and this is more a materials talk, and is about amorphous oxides and in thin film form and their impact on laser science. And so I'm Carmen Menoni. I'm a professor in the Department of Electrical and Computer Engineering at Colorado State University. And much of the work that I am going to discuss is work that we have been doing over many years in trying to tame amorphous oxide thin films grown by sputtering. Now you are all familiar that amorphous oxides are ubiquitous in many technologies, and one of them is fiber technologies. They are also used in high-K dielectrics on the CMOS circuits, and in photonics they are used essentially to create index contrast to confine light. So the reason why amorphous oxides are so attractive is because they offer a large bandgap and a large bandgap, and in addition, a high index contrast, and this is exactly what allows us to confine light. And for laser optics applications, these materials can achieve parts per million absorption loss at near infrared wavelengths. So our application of amorphous oxides is in developing multi-layer dielectric coatings. And these coatings are essentially a stack in which we combine two materials that have contrasting refractive index. So I show here a transmission electron microscope of a hafnium oxide silicon dioxide multilayer. And by selecting the materials and then selecting their thickness, then we can also tailor their optical response. And what we also accomplish by changing the relative thickness of the layers is we also can shape how the electric field, the standing wave electric field, is inside the coating. So this is how we make the coatings, sputtering layer by layer by layer. Now we have two applications for which we are interested in develop beyond state-of-the-art coatings, and one of those applications are coatings for ultra-high intensity multi-terawatt and petawatt shear pulse amplification lasers, and the other one are for ultra-stable laser cavities of gravitational wave detectors. And the materials problems that we are addressing in these two cases are significantly different. So this is what I am going to do in this talk. I'm going to briefly give you a background of what we have learned about the amorphous oxides that are synthesized by sputtering. I will talk about interference coatings for high-intensity lasers. What are the problems that we are trying to address? And then I will talk about the coatings for gravitational wave detectors. So, amorphous oxides oxides in general are essentially, you can see here they are metal bonded to oxygen, and this bonding has a specific characteristic depending on the material. And I show here how germanium bonds to 4 oxygens, forming a tetrahedron. Silicon dioxide is the same, but tantalum pentoxide is not. And then in an amorphous form, what these tetrahedra actually bond, forming rings. And And this is, in the amorphous oxide, these rings are of different sizes. Now, in an amorphous material, we know that, we lack the periodicity of the crystalline material. And so we say, oh, there is no order. But actually, there is some order in the oxide, and that order is at scales of a few nanometers. And we call that the medium range order. Now, this order can be affected by the way the material is formed. Now, recently, there has been model simulations that predict that glasses that can achieve a state that is defined as an ultra-stable state can be obtained by growing these coatings by spattering. And what is this ultra-stable state? Well, this ultra-stable state is essentially a configuration in which these rings at medium range show ordering. And this ordering is represented in the potential energy landscape as a well that has as a very deep well. So we have been studying the medium range ordering in amorphous oxides deposited by spattering. And we chose, in this case, a material, germanium oxide, that actually has a glass transition temperature of 78 degrees Kelvin, which is accessible with physical vapor deposition system. And so using Raman spectroscopy, what we did is we looked at the organization defined as the population of 6-member rings and the population of 3-member rings. And we investigated how this population evolved when we either deposited the material at different temperatures or when we also annealed. And actually, this had led us to understand, to identify that, number one, by spattering, we can form glasses that have a high degree of stability, and we see that by looking at an increase in the population of the 6-member rings. So this larger A6 over A3 ratio indicates a higher medium range order, and that is a sign of stability. So this is, here I show you how the area of the A6 peak, which indicates the population of 6-member rings, is actually affected by the deposition temperature and by the growth temperature. And what we see is that when we deposit close to the glass transition temperature, we can actually gain in improving the medium range order. Now we deposit our experiments by our thin films by spattering, and I show schematically here, the system that we use. This is, we normally spatter a metal target in a reactive oxygen atmosphere. These instruments have extreme precision to, define layer thicknesses, and we can grow multi-layers, or we can also grow nanolaminates, which are essentially nanometer thick intercalating layers of 2 oxides. We characterize our films by different methodologies, and especially what we are interested in is to understand, to identify that we don't have any crystallization, and again, we also investigate their bonding structure. And these films, as I mentioned at the beginning, can achieve impressively low absorption loss at around 1064 nanometers. There are results, especially the LIGO work has shown that in mirrors that will have about 50 layers, one can achieve an absorption loss at 1064 nanometers that is less than 1 part per million. Now, over the last few years, we have not only been deposited simple oxides like tantalum pentoxide and silicon dioxide, germanium dioxide, which are all in the amorphous state. They are called tantala, germania, and silica, but we have also been developing mixtures. And the motivation for this work was actually from the LIGO, from the LIGO work that we are doing, in the sense that we are trying to control this degree of organization. And you can do that by adding, by doping the material with another oxide. And in addition, what we have learned is that every time that we mix two oxides, we actually increase the crystallization temperature. And this is actually beneficial for both our efforts in high power lasers and in ultra stable coatings for LIGO. So this is an example of the nanolaminates that we grow. And actually we did a study in which we look at the morphology, the evolution in the morphology of nanolaminates, and we found a very interesting effect, and is that when we have, nanolaminates of a material that will have a relatively lower, glass transition temperature, then what we observe is that when we anneal, there is mixing in the thin film. Now let me briefly move to discussing what are the problems that we are trying to solve in interference coatings for high power laser. And the type of lasers that we develop here at CSU are shear pulse amplification lasers. And in this type of lasers, we start with an oscillator that produces femtosecond pulses, but of very, very low energy. And then the pulses are stretched in a Martinez stretcher, and then further amplified on power amplifiers. So they are amplified in energy, and then later compressed again with a grating compressor to obtain high energy femtosecond pulses. This is the concept for which Donald Strickland and Gerard Moreau received the Nobel Prize. So in this particular architecture, there are very critical coatings that damage before anything else. They are like the fuse to this system. And so what we are trying to address is how to increase the laser damage resistance of the coatings that go into the amplifiers and also into the diffraction grating, which are, again, if we are successful in this effort, then we will be able to increase significantly the output power. Not only the output power, but also the average power. And then in addition, we will significantly reduce the size of these laser systems. Now, in order to understand how to increase the laser damage resistance, we need to understand the mechanisms that come into play in the laser damage. And when we are above, pulse durations of 50 femtoseconds, the mechanisms of damage follow a square root of tau behavior that indicates thermal processes are dominant. However, when we go below 50 femtoseconds, then we have nonlinear processes that come into play. And so the rule of thumb in designing coatings for ultra high intensity lasers is that we need to use the oxides that have the largest band gap. And so typically these coatings are fabricated using hafnium dioxide and silicon dioxide. And they consist, again, of stacks, like I show here, in which, again, we also control the electric field distribution because we want to minimize the electric field at the interface of the coating with air. So the problems are very complex, and in the laser matter interactions, so we are looking at a multi-prone approach. We are looking at controlling the stress on the coatings, controlling the performing substrate conditioning. We are looking into new materials and looking at the interfaces. And in addition, we are working with colleagues that can do modeling to actually try this model, use this model to guide us into designing coatings that will have a better performance at 800 nanometer wavelength and 1 micron wavelength. Now, why is this important? There are a number of scientific applications that rely on high intensity ultra short pulse lasers. And I show here some of the work that our group is involved. The group of Jorge Roca is investigating relativistic laser matter interactions. And so again, here they are coupling 50 femtosecond pulses of energies, of a few joules into nanostructured targets to produce sources of extreme, that produce extreme short wavelength. These are incoherent sources that produce X-rays. And when they use targets that are plastic, then they can produce neutrons. For over a few years back, we have been using these lasers also to demonstrate tabletop soft X-ray lasers that we have used for many applications, including imaging and mass spectrometry. And there is a lot of activity worldwide in which large facilities are being developed to enable applications such as laser-driven particle accelerators, intense X-ray generation, and the study of relativistic matter interactions. So now, in the next, hopefully less than 10 minutes, I'm going to briefly describe the work that we are doing on the coatings for gravitational wave detectors. And here the materials problem, as I said, is very different, and it is related to essentially this medium range ordering in the following way. In an interferometer, a gravitational wave detector is an interferometer, and that, the mirrors in these interferometers are coated with dielectric coatings right now. And this interferometer has an unprecedented sensitivity. The arms are 4 kilometers, and the strain that this interferometer measures is of the order of 10 to the minus 21 meters per square root of hertz. If you think about it, 10 to the minus 21 is essentially 0.001 attometers. So this is the sensitivity of the interferometer. So now, if we have atoms that are vibrating in the coatings, it's going to affect the signal. And so this is something that has been investigated by the LIGO community very much, and there are predictions, that shows essentially calculate the strain noise in the interferometer, and by carefully, isolating the different sources of noise, the interferometer have been able to achieve the unprecedented sensitivity that I just described. Now, to further improve the sensitivity of the interferometer, what we need to do is we need to work on the coatings. Because what you see here is that right now, at about 100 hertz, the coatings are the limiting factor in the sensitivity of the interferometer. Now, what affects the sensitivity is the coating Brownian or thermal noise. This is a picture of the mirrors that go in the interferometer, and this is, there has been, the engineering that has gone into mounting these mirrors is just mind-boggling. But now what we are trying to do is we are trying to understand how we can control the motion of the atoms in the coatings, because that causes noise in the signal that will actually, that can shadow the signal from the gravitational waves, which is very small amplitude. Now, the two technologies that are being envisioned for coatings for gravitational wave detectors are crystalline coatings that are based on gas gallium arsenide distributed back reflectors and amorphous coatings. And right now, the coatings that are in the interferometer are a combination of tantalum doped with titania and silica. And the challenge of using the crystalline coatings is actually a technological challenge. It's not. I mean, these coatings can be easily made of excellent quality. However, the issue is that they cannot be as large as they are as a mirror is in the cavity, in the interferometer. So the coatings that LIGO presently uses are a combination of silica and as a low index layer and tantalum doped silica, titania doped silica for the high index layer. And the studies have shown that actually it is the high index material that contributes the most to the mechanical loss. And mechanical loss is related to Brownian noise through this expression. So by lowering the mechanical loss, we can actually reduce the coating thermal noise. So we have shown that, I mean, this is, part of the study that we have done, is that there are, depending on the materials and depending on the doping that we use, we can actually, control or affect the mechanical loss. And mechanical loss we can measure using a ring down cavity, as I show here. And then we can relate mechanical loss to coating thermal noise. So I mentioned at the beginning that we showed that in Germania, when we grow the material at a temperature that is close to the glass transition temperature, we get a medium range order that is enhanced compared to depositing at temperatures of the order of 100 degrees C. Well, we carried out mechanical measurements on these films, and what we showed is that actually there is a correlation between the mechanical loss and the order. And this is shown here in this plot. So what you see here is that essentially this, internal friction is again related to this medium range order. And so glasses that can achieve this ultra stable state are expected to have the lowest mechanical loss. And in fact, that's the reason why in silica we can always obtain a low mechanical loss, because that organization is much more prevalent in silica. Nevertheless, what we measure in Germania is the mechanical loss, which is 1 × 10⁻⁴, which is the second lowest to silica. So,
minutes left.
Okay, so we studied a bunch of materials and to understand how we can actually reduce mechanical loss. We studied tantalum mixtures, binary oxides, and the germanium mixture. And what we learned is that, in the tantala, when it was mixed with other oxides, we obtained the lowest mechanical loss when we use titanium, which is what LIGO has been using, and zinc. When we looked at the binaries, we confirmed that actually silica and germania, which are continuum random network glasses, they achieve the lowest loss angle. So based on this, and because Germania has such a low angle, what we decided to do is start depositing mixtures of Germania with titania and with titania, because in this way we can actually affect the refractive index. The refractive index of Germania is 1.6, but at 1 micron, and that of silica is 1.45. So there isn't that large of a contrast. But by adding titania, we can actually increase the refractive index. And we demonstrated that we can make films with a very low absorption loss as well. We carried out extensive studies of the mechanical loss and actually showed that when we have approximately 44% titania into Germania, and we anneal the sample, we can actually get a very low mechanical loss. And in fact, we have done several other studies in which, we play with the length of the annealing and the temperature. And when we go to very long annealings and a temperature of about 600 degrees C, we get films with a mechanical loss that are of the order of 3 times lower than titania dot tantala. So our colleague at Caltech, Gabriele Vagente, has done calculations that actually if we use 44% titania dope Germania anneal for 600 degrees at 600 degrees for 108 hours, we can actually, and we use this material in the design of a mirror with 52 layers, we can actually get a coating thermal noise that is very, very much, a lot of the same order as what is, expected. I mean, it will have a reduction of a factor of 2 in coating Brownian noise, which is what LIGO expects for the next generation, for the coatings that will be used in the next upgrade of the interferometer. So what will this buy us? Well, if we have coatings that have 2x reduction in Brownian noise, then we will be able to see further away in space and in time, and we will be able to learn of events that occurred, 4 billion years ago, and these type of events are measured of black holes or neutron stars. So with that, I would like to conclude, and I just would like to emphasize that that dielectric interference coatings based on amorphous oxide hold the potential to significantly advance laser science applications. Thank you for your attention.
Thank you for the nice talk. Do you have any questions? Alexei, nice to see you.
Can I ask a question? Hi, Carmen.
Hi, Alexei.
Nice talk. You described improved mechanical, thermal, optical properties of materials as applied to coatings. But I'm curious, have people who work on suspension used any of your insights into the material science? Because I know for them, for example, those fused silica suspension fibers for the large mirrors, the noise is important there. Does your science apply there?
Well, okay, this is a very good question. The fibers that are used for suspension, the same as the fibers that are used in the optical communication systems, they are made by CVD. And so when you make silica by CVD, you can actually get to what it is called this ultra stable state. So it's much easier, because the way to think about it is that in a CVD process, because it occurs, there are a couple of things that happen. Number one, the process occurs at high temperature. Number two, okay, when they make the fibers, they use a lot of chemistry, okay? I mean, a fiber is not just silicon dioxide. It has some dopants in small quantities that will actually affect that organization. So bottom line, what you have in a fiber is what we would call a material with a much higher medium range order than the ones that I can produce by sputtering. So in other words, sputtering, I mean, what I showed about Germania is the first time that it is shown that a film grown by sputtering can actually reach an organization that it is, is that of an stable glass. I wouldn't say ultra stable. There is much more disorder in the sputter thin films. So you can think, okay, they are not really glasses; they are nanoceramics. So I think that your question is, well, are they using what we learned? They don't need it because they are already making very good glasses. It's us who are not. We are not making glasses. We are making nanoceramics.
Okay, thank you very much.
You're welcome.
Thank you. The last question.
Yes, thank you. So it's interesting talk. I was wondering, because you speak about the thermal noise, but it's at room temperature, right? So how it will be when you have some new designs, they actually would like to cool to room temperatures. And also what is the relation, what is proportionally the relation of the quantum-based back action noise to this thermal noise, if you know. Interesting.
You are asking for the relationship between quantum noise and thermal noise?
Quantum back action noise, but still, this is one question about. Just I don't want to be long. And the second was basically what you describe is at measurement at room temperatures, right? But for
yes,
some
correct.
People will actually cool down the mirrors to liquid helium temperatures. So then it could be a bit different. So how important?
Yeah. Okay, I can comment on that. And it's the following. Yes. There are. You could say, okay, let's cool down the mirrors to 20 Kelvin. Okay, I mean, can we actually reduce these? Can we actually alter these processes that give rise to mechanical loss? To this mechanical dissipation, and the answer to that is no, because the mechanisms that come into play would be different, okay? And the way I need to go to my picture of the energy landscape. Okay, this picture, but let me share it again. If I can, I don't. Okay, so I cannot. I cannot share it again. But
we see it, no problem.
Huh? Can you see it?
Yes.
Oh, okay. So I'm still sharing. Okay. So so if we go to very low temperatures, you would, in the picture of, in the potential energy landscape picture, what it will happen is that we will be activating maybe some other transitions, which will be transitions between these two worlds. And these transitions between the two worlds are envisioned. This is a configurational space. So each of these, worlds represent a certain organization in the glass. So the way that this is envisioned is that at low temperature, there will be other type of, other type of mechanisms, like for example, the atoms wiggling about these, bonds within among the tetrahedron, that will actually give rise to internal friction. So the bottom line is that if we decide to go to low temperature, and there are some plans by some detectors to go to cryogenic temperatures, and in fact, I believe the detector in Japan uses cryogenic mirrors, then the materials that you need to use are completely different, because silica, germania, they all show a very high peak in internal friction at very low temperatures.
Thank you. We have to stop here and move on to the next talk. So
thank you for the invitation.
Okay, next speaker, can please set up? Can you please unshare? Okay, our next speaker will be Sergey Zurovitsky.
Hello, everyone. Can you hear me?
Yes.
Do you see the slide?
Yes. Can you make it presentation mode?
1 second. I'm trying to share. It's wrong. Sorry.
I think it was working.
Yes, I missed the screen. Do you see the presentation? Yes?
Yes. You have a laser pointer or a mouse?
The slides are changed.
Yeah.
Yes, it's good.
Do you have a laser pointer or use a mouse?
1 second. Okay. Yes. So let me start. Thank you for the introduction. My name is Sergey Zurovitsky, and I will talk about fabrication of various waveguide arrays for nonlinear topological photonics. Let me first introduce our team. It consists of 2 groups. The first group from Moscow State University, and the second one from Institute of Spectroscopy. Our MSU group provides a technological platform in this collaboration. The second group realizes theoretical part of work and nonlinear experiments. We started our joint work in 2020, and it became very fruitful. Here are a few words about the research area in which we work. The discrete diffraction and nonlinear light propagation in waveguide arrays have been studied for a long time. In 2004, the waveguide arrays fabricated by femtosecond laser writing method were demonstrated for the first time. The first experimental work on topological photonics were published in 2010s. And only in 2020, the first experimental experiments were demonstrated at the intersection of topological and nonlinear photonics. Our collaboration was started at the same time. Here I present the main points of my talk. As a member of experimental group working on technological part, I will make an accent on a laser writing technique. Then we will move on to the applications. I will show the 1- and 2-dimensional structures we fabricated and briefly discuss main results of each work. The femtosecond laser writing method is based on the following principles. When the ultra-short laser pulses are tightly focused into the bulk of transparent material, the nonlinear absorption takes place, leading to a local melting. It induces a permanent change in material structure, and in case of fused silica, the density increases, leading to an increase of refractive index. So translation of substrate relative to laser beam enables to create a waveguide. We have specific requirements for the waveguides related with our tasks. First of all, we use a titanium sapphire laser in our nonlinear experiments, so waveguides have to be designed for 800 nanometers. Second, we need low propagation loss to keep high optical power along 10 centimeters long substrate. And finally, we want the waveguide property to be independent of depth of to fabricate high quality two-dimensional structures. There are a number of parameters influencing the characteristics of the waveguide. I listed them on the slide. These parameters may influence the type of modification, shape, and contrast of refractive index, as well as losses. To describe the influence of writing parameters on waveguide properties, we considered maximum refractive index change as a main parameter of a waveguide. I will refer to that as delta n. We choose it for several reasons. It influences the degree of eigenmode localization, since we want to make two-dimensional structures the size of a single mode have to be small enough. Then the higher delta n leads to the small acceptable bending radius, and that is always good. And finally, delta n could be easily measured. At the bottom of the slide, I show a micro photo of typical waveguide, a reconstructed refractive index profile, and eigenmodes for two polarizations. Here you can see the scheme of our laser writing setup. We generate the second harmonic of the fiber terbium femtosecond laser. Then there is a feedback loop for the second harmonic stabilization. Beam expander is used to fill the input aperture of the focusing lens. Laser beam is focused into the bulk of substrate material, which is placed on three-dimensional positioning platform. All the waveguides in current work were written with a lens with numerical aperture of 0.4. I have to point out that parameters of the setup were roughly determined in advance, and after that we characterized the influence of different parameters on delta m when all other are fixed. We always start with pulse energy because it enables to determine the modification threshold. On the left figure, you can see the dependencies of delta n on pulse energy for different polarizations. The first label on legend means the polarization of writing beam, and the second one means the polarization of light injected into the waveguide. We have three observations. Delta n has a maximum near 300 nanojoules, circular polarizations. Polarization leads to stronger material modification, and delta n is higher for vertically polarized light. Our right figure shows delta n on pulse energy for 3 pulse durations. It is obvious that the shorter pulses give the higher refractive index. The shortest pulse duration is limited by the laser, so we take the minimum possible value of 215 femtoseconds. Here you can see the velocity of scan has monotonous impact on delta n. For this reason, writing velocity always has to be taken as a compromise between refractive index contrast and writing time. The right figure demonstrates the dependence of the band losses and on bending radius. It might seem that the losses are too high, but for our structure, bending radius usually about 3,000 millimeters. With this slide, I would like to demonstrate depth-independent discrete diffraction in simple waveguide lattices. The first column shows similar light distribution as the output of identical lattices written at different depths. The input beam was introduced into the central waveguide. The second column shows the microphoto of vertical lattices written over the same depth range. You can see the symmetrical diffraction pattern, meaning that the waveguide are depth independent. After some efforts focused on calibration of horizontal and vertical lattice periods, we can obtain a highly symmetrical and discrete diffraction in two-dimensional square lattice, as you can see on the right figure. Difference in horizontal and vertical periods depends on polarization of input beam. It is less for horizontally polarized light due to the waveguide ellipticity. Independence of waveguides on depth is related to low numerical aperture of the focusing lens. The top left figure shows the dependence of delta n. The dependence of delta n on the repetition rate of writing laser. There is a maximum about 0.5 megahertz, but we use a repetition rate of 1 megahertz since we didn't vary it during the initial roof parameters calibration. However, it gives us near the same refractive index as in a maximum. On the bottom left figure, I presented energy dependence of refractive index modification for different repetition rates. You can see that the higher repetition rates only the optical breakdown is possible, and there is no waveguiding. The right part of the slide summarizes the information. A set of writing parameters presented here enables us to write low loss, depth-independent waveguides with delta n of about 9 times 10 to the minus 4. Delta n is higher for the vertically polarized light, but we use horizontally polarized input because it enables better symmetry in two-dimensional structures. Now we move on to the applications of our technology. I'm sorry. The first work is dedicated to nonlinear light propagation in a one-dimensional array of trimers. You can see the underlying structures at the top right figure. First row shows an array in topological phase. Bottom row shows I'm sorry. First row shows, yes, of course, an array in topological phase. Bottom row in non-topological, and middle row shows an intermediate case. To describe the light propagation, we used continuous model based on nonlinear Schrödinger equation. The last term describes the distribution of refractive index. Middle figure shows the propagation constant spectrum for different spacings between trimers marked with the letter S, while intra-trimer spacing is fixed. You can see two band gaps for a small value of S and topological in-gap states. The states are localized on the edges of a waveguide array and depicted on the bottom left figure. There are two types of topological states: in phase, the first and second, and out of phase, the third and the fourth. You can see the sum of first two states and gives the state localized on the one edge of array, the same as the last two modes. The top left figure shows the dependence of propagation constant on optical power for out-of-phase and in-phase solitons bifurcating from linear states. Black families are stable and magenta one are not. Shaded regions shows bulk bands. The bottom left figure depicts the corresponding soliton intensity distribution. Right figure represents experimental excitation of such solitons and theoretical calculations. There are three main results. First, topological H solitons have no power threshold in contrast to non-topological case. Then we observed partial delocalization of such state when considerable nonlinearity drives the propagation constant into an allowed band, causing coupling with the bulk modes. Finally, two types of topological H solitons with different internal structures can coexist in the same or in different topological gaps. In our second work, we considered an interaction of topological modes on the edges of two adjacent dimer arrays. Top left figure shows single, top and two interacting bottom topological arrays. bottom left figure, you can see the corresponding spectrum of single and two interaction arrays. Figure E shows two corresponding interface modes. The interaction leads to power coupling between two arrays, as you can see on figure G. We designed a structure with one total coupling period on the sample length. When nonlinear recitation of one array takes place, as shown in the top left figure, we observe the possibility of coupling control via input power. It can be clearly seen on the bottom left figure, which depicts the degree of power in each array. Our observation is in a good agreement with the theory, as you can see on the right figure, and we also find that in case of interaction between topological and non-topological structures, there is no coupling at the interface. Here we move on to the two-dimensional waveguide arrays. The Moray lattice was created by the superposition of mutually rotated by Pythagorean angles square sublattices. If we consider the Moray lattice truncated by a square region, the layout of such structure presented in the top left figure. You can also see eigenmodes of such structure with different degree of localization. And the middle figure shows a microphoto of waveguide array, and we draw the common sides of two lattices with slow speed to double the refractive index contrast. The right figure demonstrates the spectrum of such structure. There are no topological modes, but there are localized states related to truncation of the underlying lattice. We obtained well agreement between the experiment and theory for different types of excitations. And in the first row, you can see the excitation of the central waveguide. There is no localization in linear regime, but nonlinearity works well. In the middle row, we excited a corner state, which is well localized even for a linear case. And the last row represents the H excitation with intermediate degree of localization in a linear region. Our results constitute the first experimental demonstration of localization phenomena induced by truncation of periodic Moray structures in photonic systems. Another two-dimensional system is rotated square lattice. You can see the consistent slices of such structure on the left figure. There are also no topological modes. In such type of waveguide array, the localization occurs as a consequence of its rotation. Rotation-induced localization arises either in the corner of the square array or in the center. The top row on the slide shows linear excitation of array with different rotation frequencies. We observed the increase of localization degree for higher rotation frequencies. The middle row demonstrates linear localization with the rise of rotation frequency. And on the bottom row, you can see a nonlinear strong light localization even for lattice without rotation. Interestingly, that nonlinearity leads to broadening of states, followed by their relocalization at high input powers. Our work is the first experimental evidence of light localization induced by the rotation of periodic structure in the direction of light propagation. In our next work, we investigated the light propagation in square lattice with periodically modulated couplings between the waveguide. You can see the scheme on the top left figure. Top right figure show the consistent slices of structure. Such structure can support localized states of topological origin at their edges, despite the fact that the lattice spans only half of the evolution period in topological phase, while during another half period it is topologically trivial. Such modes are called pi modes. Bottom left figure shows a spectrum for different amplitude of waveguide modulation, and a red line corresponds to the pi modes. Bottom right figure demonstrates the evolution of pi modes over one propagation period. There is a clear visible switching of power from outermost waveguide to the neighboring one after half evolution period. Here I presented nonlinear excitation for different waveguide modulation amplitudes. In case of weak modulation, the increase of pulse energy results first in concentration of light in the bulk of the sample, and then its gradual displacement towards the center, to corner. For modulation amplitude of 5 micrometers, the well-localized solitons form a pulse energy form at pulse energy less than 300 nanojoules, while at 400 nanojoules, strong radiation into the bulk mode occurs due to the nonlinearity-induced shift into the allowed band. At modulation amplitude of 7 micrometers, we observed the formation of the pi solitons even at 600 nanojoules. To the best of our knowledge, this constitutes the first observation of two-dimensional pi modes in photonics. In our last work, we studied nonlinear photonic declination states in waveguide arrays with pentagonal and heptagonal declination cores. The underlying structures could be obtained from honeycomb lattice by removing or inserting the sector, as shown on the top left figure. The transition from the non-topological phase to the topological one is controlled by the displacement of the waveguides from initial periodic structure. In the bottom left figure, the excitation of a declination core for non-topological case is shown. There are no localization even for high input power. The circle indicates the excited waveguide. The bottom right figure shows the excitation of well-localized topological declination state and also the formation of thresholdless soliton at declination core with increasing power. The bottom right figure shows the excitation of the waveguide not from the declination core. In contrast, we observed strong diffraction and no nonlinear localization for high input power. Now I'm finishing my talk. The slide shows the main points of report, and I'm ready to answer your questions. Thank you.
Thank you, Sergey, for a nice talk. Are there any questions? Do you have a comment or question? It looks like the comparison between the theory and experiment is very good.
Not exactly. I'm an experimental man. I just try to understand what do our colleagues.
Okay, so do you have
No questions.
no?
If somebody have any, you can send it at email.
Yes. Then let's get back to the next speaker. Let's thank one more time, Sergey.
Thank you.
Next speaker. Next speaker will be Irina Tereshenko.
Hello. I'm trying to share my screen.
Yeah, I can see your slides. Let's put them to the presentation mode. Do you have a laser pointer or?
Oh, I will use mouse.
Okay. Okay. Thank you.
Okay. Hello, dear participants and listeners of the conference. My name is Irina Tereshchenko, and first of all, I would like to thank the organizers for the opportunity to give a talk on this conference and to present my results. And my work is devoted to the analysis and of the excitation dynamics in two-dimensional semiconductor nanostructures induced by a quantum electromagnetic field under the Kerr phase modulation. Those studies are relevant from the point of view of the new possibilities to control the localized excitations and currents induced by quantum electromagnetic in solids and especially in two-dimensional material, what is very promising for the development of quantum information technologies. Moreover, the interaction with non-classical light and the transfer of non-classical properties and even quantum correlations from photon to the electronic subsystem open up new prospects for the analysis of hybrid electron-photon systems and provide the basis for the development of a fully quantum photon-matter interface, which is very promising, especially if nanosystems are implemented. As another example of an application, we can cite the diagnostic of two-dimensional materials, which is based on spectroscopic analysis using the methods of Raman spectroscopy. It is known that in such materials, exciton formation makes the main contribution when interacting with light. And for the correct interpretation of experimental Raman spectra and conclusion about the state of the surface and the thickness of the material, it is necessary to correctly take into account all possible channels of exciton formation. And the theoretical approach presented in this paper is the basis for the development of the correct analysis methods. For now, hybrid systems are already treated in experiments in which the solid-state nanostructure interacts with the quantum field. And this is often implemented in solid-state resonators since they provide good interaction of non-classical field with the nanostructure, and therefore the following unsolved problems arise. So the first is analysis of peculiarities and search for new effects caused by the influence of the quantum field. And the second is consideration of nonlinear effects which arise in solid-state systems and dramatically influence on the excitation process. So the subject of the study is the formation of excitons in the planar nanosystems located in microresonator or cavity. In our work, the formation of excitons described in terms of bosonic ladder operators responsible for creation and annihilation for an excitation. Therefore, exciton states can be considered within the framework of the quantum harmonic oscillator model. In the case of single frequency field, the nonlinear Kerr cell phase modulation is taken into account, while for two spectral field modes, the cross-phase modulation effect is analyzed. And the theoretical approach was based on solving the non-stationary Schrödinger equation using a wave function. We solve a differential system of equations for probability amplitudes. So let's come to the results. In the case of absence of nonlinearity, different excitation channels are characterized by populations oscillating in time with constant frequencies and amplitudes, and no modulation of time-dependent behavior of the excitation probability can be found. However, even a small nonlinearity leads to the appearance of different dynamics of each channel and the appearance of modulation, while different channels are characterized by different modulation, which makes it possible to better separate the excitation of those channels by time. And this is very promising for practical applications. Next, the existence of different regions of excitation dynamics was discovered depending on the characteristic parameter K, which actually compares the nonlinearity and strength of the interaction of the field with the electronic subsystem. And for rather low nonlinearity, when the parameter K is much less than 1, a strong coupling between the electronic subsystem and the field provides the Verbi-like dynamics of excitation and periodic efficient population of the highest excitation channels. And this fact is illustrated by two-dimensional plots of the time-dependent probability of different excitation channels presented in figure A and C for initial number of photons in the field 2 and 5 respectively. So if the nonlinear interaction prevails, so when the K is more than 1, the excitation of the high order channels appears to be suppressed. So we should see figure B and D. In addition, in the case of strong nonlinearity, the interaction period is significantly reduced. So it could be expected that the presence of nonlinearity would lead to large suppression of different channels, but this is not always the case. For a more detailed analysis, probability distributions were constructed depending on the nonlinearity parameter and time, from which it can be seen that for each channel, you can choose an optimal nonlinearity parameter, at which the maximum probability is realized, even higher than without the nonlinearity. However, for the highest channel, the distribution structure is such that, as can be seen from the figure D, it collapses near zero. Therefore, by changing the nonlinearity parameter, it's never possible to threaten this channel, at least simply from the law of conservation of energy. However, those distributions are presented only in the resonant case. The presence of frequency tunings also leads to the possibility of controlling the excitation. Thus, with the help of the law of conservation of energy, a formula was analytically obtained for finding the optimal detunings for any channel, ensuring the maximum possible excitation of even the highest channel. Thus, to enhance the highest excitation channel becomes non-possible by varying the field frequency detuning. Also, additional values of optimal detunings are also found for intermediate channels, and their analytical estimations are obtained. However, the width of those frequency maxima may be different depending on the system parameters. Thus, they may overlap with each other, resulting in interference effects, as shown in figure C. And physically, several side peaks can arise when not only the required channel, but some other channels are involved in the excitations. Well, interesting results were also obtained under the influence of a quantum field, which is a superposition of Fock states. So coherent and squeezed states were considered, for which the excitation distributions of the electronic subsystem were analyzed. And due to the energy exchange, both the photon statistics and the relative phases are transferred from the field to the electronic subsystem. So the figures demonstrate the formation of a photon-like non-classical coherent or squeezed exciton states of an electronic subsystem. And the creation and controlling of such states seems to be the basis for the development of various quantum information algorithms. However, such situation is possible only in the case of absence of nonlinearity. In the case of nonlinearity, the situation gets worse. So the slide shows two-dimensional time distributions of excitations, and the upper two distributions correspond to the case of low nonlinearity, while the lowest ones are obtained at larger nonlinearity. So it can be seen that the efficiency of excitation of channels is decreasing, and only the lower channels are excited. And it's possible to partially reduce the negative role of nonlinearity by choosing the optimal detunings, and distribution taking into account the detuning are shown on the right side. So it can be seen that it is really possible to achieve good excitation of the upper channels, but it is mainly achieved at the initial stages of dynamics. Next, we will proceed to the results obtained for the interaction of a nanosystem with two field modes in the presence of the nonlinear cross-phase modulation. And the slide shows two-dimensional distributions over different excitation channels of the electronic subsystem, it's A and C, and populations of different Fock states of the field mode, it's figure B and D. So in the case of absence of nonlinearity, it's A and B, and the presence, so it's C and D. The cross-phase modulation is seen to play a negative role and suppress the excitation of highest channels. At the same time, a very non-trivial field state is formed during the interaction, which is characterized by population of Fock states neighboring to the initial one. And this absurd effect is possible due to the energy exchange between the field nodes via the coupling with electron subsystem. A rather specific distribution of excitation was found in dependence on the field frequency detunings, and due to the effect of the cross-phase modulation, two optimal frequency regions symmetrically detuned from resonant are found to provide maximal excitation in the nanosystem. And in contrast, the similar distributions obtained for the field nodes population, and they appear to be neurosymmetrical and reveal much lower optimal detunings. Another interesting result concerns the effect of the field mode correlations on the excitation process. So we consider the entangled two-mode squeezed vacuum states, and the wave function is represented as follows. So the initial diagonal-like distributions of this state over different Fock states is shown on the slide, and it's characterized by strong photon number correlations in field modes. Only equal photon number states in both modes are populated. So it can be seen that in the absence of nonlinearity, the population of even excitation channels dominate due to the photon correlations and possibility for two photons, and I mean one from each mode, to participate simultaneously in the excitation. It's about point A on the figure on the right side. And in such a process, a chessboard field distributions is formed, and the point B corresponds to only one photon excitation. So it means from one or another mode, which has much lower probability and is characterized for the following photon number distribution in two modes. Next, if cross-phase modulation is taken into account, single photon processes are enhanced since the effect of photon correlation is suppressed, and the presence of nonlinearity makes a negative contribution to the correlations of field modes. So synchronity is broken. And however, for small values of the nonlinearity parameter, the discussed above photon number distribution in two modes can be observed. And finally, I come to the results, and I will summarize it. So first, the different excitation channels are characterized by different modulation, and the possibility to separate channels in time is demonstrated. Then different regimes of excitation dynamics are found in dependence on ratio between the nonlinearity and the parameter G, which is compares the threat of the interaction of field and field with electronic subsystem. And next, the nonlinearity is found to enhance the excitation of different channels. One more interesting result is that the possibility to control the excitation by varying the frequency detuning is demonstrated. Then an optimal detuning was found for each excitation channel, and an analytical formula for its value was obtained. Then the formation of non-classical coherent or squeezed exciton states of an electronic subsystem is demonstrated, and which is the basis for the development of various quantum information algorithms. And then the effect of field mode correlation on excitation is revealed. So thank you very much for your attention. If you have any questions, I will be ready to answer.
Thank you, Irina, for the talk. Do you have any questions? I have maybe a quick question about the time. What is the time unit?
Yeah,
Dynamics.
I understand your question. So the 1 point, like 1 second, is 0.1 of the Rabi frequency, which is actually no more than 1 picoseconds. It is connected with the time life of the photon, which is in the solid state resonator, which we analyze in this work. It was in the beginning slides. I will show you, this picture. So if I'm not mistaken, the lifetime of the photon is 11 picoseconds. So the time is. Do I answer on this question? Was it?
Yes, it's on the order of picosecond. Yes.
Yeah.
But for the experiment, are you thinking about using this system to put a MOS2? This was a different. This was a.
I'm sorry, the connection wasn't really good. Can you please repeat the question?
Okay, can you hear me now?
Yes.
You work as a theoretical, and are you planning to do? Are you planning to do some? Anybody planning to do some experiments on this work? Are they planning to use a similar system that you show right now on the slide to put MOS2?
Well, I don't really know. So I know that there are some theoretical groups who are who investigate the same topic as my group, but we do only theoretical work. But maybe then they will do some experimental things. But I know that they try to communicate with us, and so we discussed some interesting details. But I don't remember that someone wanted to do some experience.
Okay, well, I hope soon.
So can I stop sharing?
Yes, please. Thank you. Okay, anybody else? No more questions? Let's thank Irina one more time. Thank you. Okay, let's proceed with the last speaker for today.
Okay, can you see?
Yes, I can see the slides. Okay. Yes.
And okay. Oh, sorry.
Do you have the laser pointer or the mouse?
The mouse. Can you see my mouse as well?
Yes.
Okay, great. So hello, my name is Cole Reynolds. I am one of Vitaly Kocharovsky's graduate students in the Department of Physics and Astronomy at Texas A&M University. And today I will be discussing talking about degenerate bound states in the continuum and a grading waveguide. So the method of infinite grading eigenmodes versus the numerical rigorous coupled wave analysis, also known by its acronym RCWA. And to preface this talk, I'd like to state that the study of bound states in the continuum is dominated by this RCWA method, right? And essentially, if you don't, someone doesn't know what a bound state in the continuum is, it's essentially the localization of a field, depending on whatever your field is, electric, matter field, the localization of this field at certain frequencies or energies in its continuum spectrum. So to sort of emphasize or to sort of maybe elaborate, if we take, and we're talking about waveguides here, so if we consider just a homogeneous slab, waveguide is seen or depicted on the left. If you shine light at it, it'll never get trapped. It'll always either be transmitted or reflected, and it can never be trapped inside. So these homogeneous slab waveguides can never be bound states in the current, because even if you change the frequency of your light, it'll never get trapped. But on the contrary, a grading waveguide is depicted in figure A, or if we just add a second permittivity to the slab, and it's now this grading waveguide, we actually can construct or reveal bound states in the continuum. And so this is the next simplest system other than a homogeneous waveguide. And so now at this point, RCWA would how they would construct, I guess, the analysis is you would go and you would decompose your permittivity's spatial profile. So here we have the period, it's epsilon 1, epsilon 2, it's periodic, so it has a Fourier coefficient, the series coefficients, and you would take as many coefficients as you want. You would approximate this structure to some arbitrary degree of accuracy, and then you would solve Maxwell's equations. So already you don't even, no matter how many Fourier terms you take, you'll never even have the full grading structure. You won't have your full potential to begin with. Now, contrary, if we use our method of infinite grading eigenmodes, all we do is we consider the boundary conditions in the longitudinal direction, and we use the Bloch's theorem, and we find that the modes or the eigenmodes that can live inside of this grading, right? And that's independent of, that's simply in the longitudinal direction, so no care for the thickness L or the permittivity of the cover and the substrate. Right now, where the permittivity of the substrate cover and the thickness come into play is with the guided modes of the slab, the homogeneous slab waveguide on the left. So for a guided mode, you do need to solve boundary conditions, and that does involve the thickness, the permittivity of the cover, and the permittivity of the substrate. Now, outside of your grading, outside not of your slab grading in the cover and substrate, we simply decompose the infinite grading eigenmodes into their Fourier harmonics, right? And so to sort of compare the two, for the grading waveguide, the pth, as it's seen below in figure B, the pth Fourier harmonic will radiate in the cover or the substrate if the permittivity of the cover or the substrate is greater than this quantity here. So now note that the 0th Fourier harmonic, or just a constant function, or the constant term, will always radiate in the cover or substrate. But we can choose permittivities and frequency, or normalized frequency of omega times lambda grading divided by c, such that every other Fourier harmonic will be evanescent, or will decay, so it won't propagate. So we can construct a system such that we only need to care about the 0th Fourier harmonic. And so, and in particular, we care about the waveguide eigenmodes. We care about some weird combination, or not weird, but we care about a specific combination of these infinite grading eigenmodes that can then form some sort of linear combination that can then act as a guided mode, and as depicted by like a homogeneous slab waveguide. So we want to pick certain infinite grading eigenmodes, and we want them to not couple with the radiation channels. And that would essentially, if we can do that ideally, that would be a balancing continuum that the field or the light will never leave, and it'll be completely localized. So this is the method that we're trying to take advantage of, and we want to do so through analytic methods. We don't want to use sort of numerical approximation. So on the right, we have the dispersion curve of the infinite grading eigenmodes, and the parameters are stated in the figure, or in the figure caption below. So we've chosen our epsilon 1, epsilon 2, and we've chosen the specific fill factor, or rho, such that we have a degeneracy point, and I guess labeled by D023 here, at this frequency 4. So what it means is that the second and the third, in this case, infinite grading eigenmodes, if we sort of count down, they have the same Bayesian squared value at this frequency. Okay, so now on the left, what we have is a dispersion curve of the guided modes. So these guided modes in this figure, if I go back a slide, the homogeneous slab waveguide in figure C, we have these guided modes. This is the dispersion curve on the left for the guided modes, and inside the blue region is where they are actually guided. So they're not radiated and they're not evanescent. So they're guided in this region, and we see this sort of hierarchy of this enumeration. And the result here is a series of transverse modes, and they have the corresponding spatial or transverse profile depicted on the right. So for n equals 3, we see we have 3 sort of peaks, and for n equals 2, we have 2, and for n equals 1, we want. So this is all somewhat standard, and we've chosen these parameters down here. Epsilon of the cover is 1, epsilon of the substrate is 2, and the thickness depicted below. Right. So now a waveguide eigenmode would be the combination of both of these two. And we can do so through just the theory of the infinite grading eigenmodes. And what we see is that when we solve for these waveguide eigenmodes depicted on the right, they come in pairs, and I'll discuss the pairs and their ordering in a second. But I'd first like to talk about the plot or the figure on the left. What we have on the left in the blue, so the sort of contour plot, is a RCWA sort of resonance response. So you send in some type of signal or field, and we see what modes are excited or what fields are excited when we send in some like a variety of or some certain profile. And superimposed on top of that in the dashed colors, these dashed lines, is this exact dispersion curve on the top for the guided modes, except we've reduced them to the first Brillouin zones. We sort of folded them on top of each other, so it only extends to pi. So on this figure, it goes pi on the left, but here we've kept it just to a pi. So we fold them back in on themselves, and we see on the right. So now going to the right, we can look at these waveguide eigenmodes, and we can see sort of a direct ordering or a comparison with a combination of these infinite grading eigenmodes and these guided modes that you would see in this homogeneous slab waveguide. In particular, so for example, in the green, the very top one, it's 3 sort of peaks, because it corresponds to the n equals 3 guided mode. So we see the 3 peaks, and then we see the single peak for n equals 1 and the 2 peaks for n equals 2. And so the red represents n equals 2. And if we sort of, and these are sort of ordered to be the same sort of depiction. So for the first and the third, those are the black sort of intersections, dashed lines. We see that they only have 1 peak. The reds, they have 2, and the green at the top, it has 3. Right. So this all, and it's sort of very coincidental how much this dispersion curve of the grading waveguide corresponds to the dispersion curve of a homogeneous waveguide, homogeneous slab waveguide, if you just use the average sort of permittivity. Now, but were they both, these infinite grading eigenmodes are sort of forced to obey or forced to conform to the boundary conditions of these guided modes. But the boundary condition of the guided modes is purely a phase condition. It just has to have some sort of 2 pi multiple phase condition. It says nothing of the amplitude of the infinite grading eigenmodes that has to be sort of preserved. You don't have to preserve that. And this is where we see the sort of split, why there's 2. And if you look at, for example, this bottom one that's ordered 1 or labeled 1, 1, we see that on the left we have a mode profile that is odd with respect to the center of each section, and on the right we have one that's even with respect to each center, and the same for the one above that for 2, 1 as well. And these are the 2 that are depicted by these sort of circles on the left plot, and the bottom one corresponds to a symmetry protected bouncing continuum, and the top one corresponds to a degenerate bouncing continuum. Now, what differentiates a bound state in the continuum from a high Q waveguide eigenmode, and if I didn't mention a high Q waveguide eigenmode, is simply the waveguide eigenmode that maintains its amplitude, that maintains more of its amplitude after it does a full round trip in the transverse direction. So it propagates up, reflects, propagates down, reflects. But these symmetry protected bouncing in the continuum and this degenerate bouncing in the continuum, these bottom 2 plots on the left, they I guess, ideally maintain a unity amplitude. Their amplitude actually doesn't change, so it is completely trapped. Whereas the 3 above, they have some slight coupling to that 0th Fourier harmonic. So these bottom 2, or these bottom left 2, have 0 coupling to the 0th Fourier harmonic or the radiation channel. So we'll first specify this bottom one, or the symmetry protected bouncing in the continuum, and we see. If we zoom in on that dispersion curve on the left, this RCWA analysis, where we see on the bottom, or before actually we look at the dispersion curve on the left, we first just look at the infinite grading eigenmode profile of the two, right? We see a very clear distinction between the third, or what we enumerate to be the third, and the second. So the second is even with respect to the center of each section. So the second has a peak in the middle, and the third has, well, it's equal to 0 in the middle, right? So, and what we can see is if I sort of try to project the third, this F3, if I just try to project this mode F3 with the 0th Fourier harmonic, or the radiation channel, just a constant function, this mode F3 is odd. So its integral over the period will give you 0. So it has no coupling. And that's exactly what we see in this top left figure here. So this is the coupling to the 0th Fourier harmonic, the radiation channel. And what we see is on this top branch, that when kx is equal to 0, we have 0 coupling. It disappears. It goes from some large value to some very small value. It's very clear that it decouples. But we see on this bottom plot, this top branch, well, there's only one top branch, and I'll state why in a second. But we see that for this top branch, the third, this top branch is the coupling or the reflection amplitude back into the grading. So it very strongly reflects back into itself. And it has 0 coupling to the, we see here that it has 0 coupling to the third, or to the 0th Fourier harmonic, or the radiation channel. Now, conversely, if we look at the second mode, we see that it's odd, and so it's very leaky. If I integrate this, if I just integrate this function, I'll get something non-zero, because, well, the peak, the top part is much larger. The area under the curve is much larger than the area for the negative part, and so we see that it does have some coupling to the radiation channel, and that's why we see that nowhere does it completely lose its coupling. It looks like this line is still, there's some faint white line, but it never completely loses its coupling. And we see that the third infinite grading eigenmode, if we look back on this bottom figure, it never interacts or couples with that this F2 mode. So they're completely independent of each other in this regard. Now, this is in stark contrast to if we now look at the degenerate balancing continuum, so the one at frequency 4, there were these red dashed lines intersect. This is a set, although it appears that the structure, it's just the next continuation where I just add in a separate period or a peak in the transverse Z direction. But instead, the profile on the left of this dispersion curve, it's completely, well, it's not complete, but it's fundamentally different. There is no separation or gap in the frequency. It's a complete cross. And so what we see is that there's actually sort of two things happening here, or there are two waveguide eigenmodes existing at this exact same frequency. What we have is a high Q mode being sort of shadowed or drowned out by the resonance or the coupling to the radiation channel of the low Q mode. And so this is still the second and the third infinite grading eigenmodes that sort of construct this resonance here. But at the bottom, we see the real component of both the second and the third just by the re of F. And so those are both even, but the imaginary parts of both are odd. And so both of them have coupling to the 0th Fourier harmonic, so they both radiate. But the fact that they're at both frequencies, but what we can do is, instead of it being sort of a basis of where the leaky mode is with one infinite grading eigenmode and the high Q mode is with some other infinite grading eigenmode, it is now some sort of superposition, some in-phase and anti-phase superposition of these infinite grading eigenmodes, where the anti-phase superposition, so if I take the difference between these two, right, the real part cancels out, and all I have is an odd imaginary part. That is our bound state in the continuum, because it's integral, right? Its area under the curve sums to 0. But the real part exists at the low Q part, which is composed of the real part, exists at the exact same frequency, and so this bound state of the continuum is hidden. Now, to investigate the sort of profile of this degenerate one a bit more, if we zoom in on this dispersion curve, if I sort of go back, if we zoom in on this D0 to 3 point here on the top left, we see sort of what happens once we change the enclave wave number slightly, this kx times lambda grading value. If we change that slightly, we see this sort of anti-crossing schematic between the blue dashed and the red dashed. But when kx, or the in-plane wave number, is equal to 0, they have this fundamental crossing. So what we do is we sort of pick the limit when this in-plane wave number becomes 0. And if I plot just the spatial profile of the second infinite grading eigenmode as seen in B here on the right, what we see is that for negative frequency detunings, or negative frequency tunings from this critical point, or this resonant point, we see that it has this even profile. But as it crosses through this point, it undergoes this sort of symmetry breaking. And the symmetry breaking is actually what gives rise to this bound state and continuum, because we need both of these infinite grading eigenmodes to construct this high Q and low Q bound state in the continuum. So the third would just be sort of a mirror image of the second. And to sort of show, sort of compound what I stated, if we look at figure C, what we see here is they're coupling to the 0th Fourier harmonic. And so in the dash for a higher in-plane wave number, and the solid for a lower in-plane wave number, with the colors representing the second and third infinite grading eigenmode. And so we see that independent actually of kx at the resonant point, they will always have the same coupling to the 0th Fourier harmonic. So the anti-phase superposition will always be this high Q mode, and the in-phase superposition, where we just add the two together, will always have the low Q, because that coupling will be added. And correspondingly to the right in figure D, what we have is there's a Q factor of this high Q mode. So, and the function that it is approximated by, well, here just for the sake of brevity, is depicted on the right. But we see that it's proportional. The Q factor is proportional to whatever in-plane wave number you choose. Well, 1 over that squared. So that, well, not proportional, but that's the maximum value you can have, because of course the frequency detuning and the kx detuning causes all these other sort of detunings that will allow them to decouple, or will allow them to not be perfectly asymmetric from each other, and will allow them to couple to other modes that couple to the radiation channel. So, and this is completely unseen by the rigorous coupled wave analysis, because they'll look at the outputs and they'll see that this present is always there. They don't know how to sort of dissect, because it is standard to sort of look at different frequencies. They usually don't have this type of sort of intersection. They have similar intersections, but you very rarely, when we've seen, see a degenerate type of mode. And when I say degenerate, they're not completely degenerate. They have separate Q factors, so the high Q and these low Q modes are not completely degenerate. They sort of pass each other in the complex plane, whether it's their Q factor or whether it's their phase profile, because even their not phase profile, their spatial profile, even their spatial profiles are different. We call them degenerate, but we simply mean that they have the same, when projected onto the real axis, they have the same Kasian squared and the same frequency value. So in conclusion, using these analytical methods, we with much more ease and computational power, relatively none compared to rigorous coupled wave analysis, we reveal an origin in this fine structure of the degenerate bound state in the continuum, formed by the crossing of these infinite grading eigenmodes, undergoing the spatial symmetry breaking in this near vicinity of the degeneracy point. This was all taken. We did perturbation about this degeneracy point. So now, but in general, the numerical rigorous coupled wave analysis is not enough, because you'll never see this sort of symmetry breaking in this high Q mode, because it'll be overshadowed by the existence of this low Q mode. You won't ever get this sort of splitting of the two. They exist at the same real frequency. So to clearly see the structure of this degenerate bound state and continuum in low Q waveguide eigenmodes, you were required to use analytical methods that, considering just the first few propagating infinite grading eigenmodes, because we only need the first few propagating ones, or actually we only need the propagating modes, which is a small finite value, to sort of understand the rich structure that's going on. And the RCWA method is forced to use, depending on the accuracy that you want, these unboundedly large matrices to do your computation. So it just seems that not only are you losing accuracy because you're not properly describing your system, but you're forced to exhaust a lot more computational power to sort of do something that at least in our opinion, isn't even as accurate. So, and we have a paper in the archives listed below that sort of discusses this in preprint. And I think that would more or less conclude my talk. But I'd like to quickly thank the Raba family and the William A. Raba Endowment for funding my current research. And so with that, I believe I'm done, and I guess I'm open for, or I invite all questions. Let me try to, okay, I can just do that.
Thank you, Cole, for the talk. Any questions?
I guess people are tired.
The talk is clear.
Oh, I can.
No. If anybody have questions, we can post them later.
Yeah.
So our conference and our seminar comes to the end. Thank you, Dmitry, for chairing the last session, and thank you everybody who stayed with us for the last session. Everybody is welcome and invited who stayed till the last talk for the next conference. And while it was a long week, we had 72 talks in our seminar. We learned a lot of new things. And I hope that next time we'll be able to meet in person in some good place. And I wish you a very nice weekend. Bye.
Thank you, Olga. Thank you for organizing everything.
Thank you. Thank you, Dmitry.
Thank you, Olga, and congratulations. This is a good accomplishment.
Thank